Well, good afternoon. I'm sorry I am not able to be there on in-person venue, but I do want to introduce my PhD student, Venue Ren. He's a fifth-year PhD student who passed successfully his preliminary exam, and now he's working towards his final PhD thesis and worked on exciting research to understand anomaly detection, causality of various smart grid failures coming from the generation systems, and then providing explainable and actionable intelligence for many events and alerts that are coming from the generation system. So please welcome Venue Ren and his presentation on these exciting topics.
Okay, thank you, Clara. Hello, everyone. Just as Clara introduced, my name is Venue Ren. I'm a PhD candidate in the Department of Computer Science in UIUC. Today, I'm very glad to present you the current progress of our current CRUST project, ADNA, Online Context-Aware Intelligent Framework for Anomaly Detection and Analysis in SCADA Networks. Other researchers in this project include my advisor, of course, Professor Clara Nashad, and Tim Yardi. Both of them are from UIUC. So please feel free to interrupt me if you have any questions during the presentation. So a SCADA system is a common industrial control system, which is used to collect data from sensors located at remote sites and to issue commands from a central site for control purposes. The major components in SCADA system include the master terminal units in the control centers and the field devices in the remote substations, and also the communication networks which connect them. So since SCADA is usually deployed at critical infrastructures such as power grids or oil refineries, it is therefore a common target for various attacks. There are many works concentrating on anomaly detection and security of SCADA systems. However, there are many problems with existing solutions. On the one hand, most of the existing solutions usually fail to utilize all levels of network data in proper ways. And on the other hand, most previous works do not provide further analysis of anomaly being detected. So for the first problem, data in the SCADA networks generally can be divided into three levels: the transport level, the operation level, and the content level. So the transport level data refers to traffic flow statistics, which you can find in the transport layer headers in the packet. And operation level data usually refers to operation statistics in industrial control protocols, such as what operations the industrial control protocols are carrying. And the content level data refers to measurement statistics from the field devices, such as like what measurements do you get from those field devices. And most of the existing solutions only focus on monitoring and event detection of one or two of the three levels of data, and which is not enough to detect and reason about attacks in all three levels. Also, data in different levels have quite different characteristics, which requires different methods to deal with. But existing solutions usually apply the same method to different levels, failing to take data characteristics into consideration when selecting anomaly detection method. And for the second problem, the focus of most existing work is only turning data into knowledge by performing event detection on network traffic. And there's a lack of further analysis of the anomaly detected. Since the cause and consequence of the event are not identified, it is very hard or even impossible for the operator to quickly digest events detected and react to it. So in this project, to target the two previously mentioned problems, we aim to design an online context-aware intelligent framework for anomaly detection, cause and consequence analysis, and response suggestion for SCADA networks. And to target the first problem we mentioned before, So we built a multi-level anomaly detector to monitor all three levels of network data. And based on the distinct characteristics of data in various levels, we actually propose different anomaly detection methods to apply to different levels of data. And for the second problem, which is the failure to do further analysis on the anomaly detected, we actually intend to follow the path of turning data into knowledge and knowledge into understanding, and finally understanding into action. So our framework has the capability of not only detecting anomalies, but also analyzing cause and consequences of anomalies, as well as suggesting feasible responses. So here, I will use a DOS attack example to better illustrate the path and steps of our approach. So first,
can I ask you a question?
Sure.
So is the final objective a tool that you will be developing as part of it? Is that the final objective of your work? Is it going to be a tool that can actually do all that? Or
yeah, we will build a prototype of the framework. Yeah.
Okay, thanks.
Yeah, and we will test on some of the simulated data we have from our ITI test bed. Yeah. Yeah, but this is the work in progress, so we are currently working on that part. Yeah, so let me now use this DOS attack example to better illustrate the path and steps of our approach. So first of all, we use network sniffing to capture network traffic as our data. Then we perform event detection, which can help us to turn data into knowledge. And by that, we can find some packet increase in certain flow. And after that, we conduct causality and consequence analysis, which help us to turn knowledge actually into understanding. And by that, we identify the DOS attack and infer that the cause is a compromised node probably, and the consequence is a denial of service. And finally, the response suggestions helps us to turn understanding into action. So the suggestions of traffic filtering and node neutralization is provided to the operator. And this is the architecture of our framework. So there are several components in our framework. They are all modularized. So first of all, there's a probe component which monitors the network traffic and forwards all three levels of network data to the anomaly detector. And the multi-level anomaly detector then use proper methods in different levels to detect anomalies in different ways. And after the anomalies are detected, the multi-level anomaly detector actually generates alerts. And those alerts are forwarded to the alert manager. In the alert manager, the alerts are aggregated and also prioritized. And all the previous three mentioned components, the probe component, the anomaly detector, and the alert manager sit at the edge of the network, which is usually in the substation in SCADA system. And after the alert is prioritized, it is actually sent back to the control center for further analysis. And in the control center, there's a causality-based anomaly analyzer, which actually takes domain knowledge and cyber physical model into consideration and analyze the causes, consequences, and of the anomalies detected, and also provide potential responses to the operator. And we further divide this project actually into two sub-projects based on whether it's on the edge or at the center. And we are actually currently working on the first sub-project, which is the edge components, the design of the edge components. And at this moment, we're still in the implementation phase of the project. So the evaluation has not been done yet. So in the following, I will just describe the design of the edge components. Now, please let me describe the design of the anomaly detector and the alert manager, respectively. The structure of the multi-level anomaly detector is shown in this figure. There's a listener, which actually captures the data from the probe component and forward them to different levels of anomaly detectors. And in each of the anomaly detectors, there's a parser, which helps to parse the data, the Bro data. Because Bro has its own data structure, we need a parser to translate that data to data we can use by further analysis. And in each of the anomaly detector, we also have 1 or 2 processors which actually apply the anomaly detection method. And it is a processor that actually finally generates the alerts. And before I describe the design of each processor in more detail, I will first briefly introduce a concept named confidence score in our work. So basically, we give a confidence score to each of the alerts we generated, and we actually define the confidence score to be the confidence that the corresponding alert is actually an anomaly. And the score is between 0 and 1. And it can be calculated by the product of 2 parts. The first part is the model accuracy, and the second part is the anomaly score. The model accuracy is actually the accuracy of our model in describing normal behavior. And we actually use the sigmoid function of their data sample number to estimate this model accuracy. And the second part, the anomaly score, is a score which helps us to measure how far does the current value deviate from the normal behavior. And like as I said, different levels have different methods for anomaly detection, so they use actually different ways to calculate this anomaly score. And the confidence score is actually the product of these 2 parts. So let me now introduce the detailed design of the anomaly detector, the transport level anomaly detector. The parser is very straightforward, so I'll just ignore it. And the objective actually there are 2 processors in the transport level anomaly detector. One is the packet processor, which actually runs for every packet it receives. And there's also a flow processor which runs for every period T flow. Actually, this is like the aggregated version of the packet processor. It will like first aggregate a bunch of packets together and do the anomaly detection on the aggregated statistics. And so the input data for each of the processors actually consists of several types of fields. The first type is the index fields, which includes both of the index fields of the input data for the 2 processors include the originator for the connection, the responder for the connection, and the transport protocol used by the connection, and the port number. And as you can see, those 2 processors share the same set of index fields. And also, like they are also like our data fields, which actually are the data we do anomaly detection on. And the data fields for the packet processor include the inter-arrival time of packets and also the packet size. And the data fields for the flow processor are the packet count during that period we actually aggregated. And actually, these 2 processors use different methods for the anomaly detection. The packet processor uses a simplified 1D version of a clustering method called the downstream. This is like a clustering method in the existing work. We actually modified it and used a 1D version of it. And the flow processor actually just used mean and standard deviation as statistics to do the anomaly detection. And we utilize the Chebyshev inequality to help us to calculate the anomaly score. We use the same method to calculate the anomaly score in one of our previous works. So as I said, one of the design decisions we made is to apply proper methods to data with different characteristics. So here is an example, actually, because for the packet processor, the data field are inter-arrival time and packet size, which usually actually follows multi-model distribution. For example, considering the packet size, if you have a read request and also you have a confirmation, both from the same node both from the control center to one of the field devices, They are both considered valid traffic, but they have quite different. They can have a quite different in packet size. So actually, those interrupt time and packet size can follow like multimodal distribution. So therefore, we actually use a clustering method to do the anomaly detector. But the packet count for the flow processor actually is usually unimodal distribution. So we actually can simply use the mean and standard deviation. They are good enough to characterize the normal behavior. And now let's move on to the operation level anomaly detector. So the objective of the operation level processor is to detect anomalies in the operations of industrial control protocols, for example, Modbus and MP3. And here, the input data also has several index fields, such as the originator, the responder, and the industrial control protocol, and finally the unit ID inside of the industrial control protocol, which helps to differentiate the field devices which share the same IP address. And this index field actually here serves as key, and the data field is like the value. And here we also consider the inter-arrival time for the same operations. And in this level, there are usually two types of anomalies. One is the invalid operations, which include, for example, invalid function code and maybe wrong direction of the operation, for example, a command sent by the field devices or etc. And for this type of anomalies, we can simply use rules, predefined rules to check against and to find those anomalies. And another type of anomaly is abnormal operation, which includes, for example, some new operations emerges, or some existing operation disappears, or there's some like abnormal inter-arrival time between two operations. And for this kind of anomaly type, we can use statistical ways to detect. And we here still use the mean and standard deviation because we consider like the operations in the SCADA system usually follows a unimodal distribution in terms of inter-arrival time. And the content level anomaly detector, which is also the most complicated one among the three. So the objective of the content level anomaly detector is to detect anomalies in measurement values which are included in responses to read requests. So those are actually the measurements collected by the field devices and sent back to the control center. And as usual, the input data has a set of index fields here, such as the holder, the IP of the holder of the measurement, which actually is the IP of the field devices which send the measurement, and of course the industrial control protocol, the unit ID, and the measurement type, and finally the measurement index. And the data field here is simply the measurement value. And since we have different types of measurement here, and we actually apply different methods for different types. Take DMP3, for example. There are three measurement types: binary, analog, and counter. So here we'll take the binary and analog, for example, which are also the most commonly seen measurement types. So for the binary measurement, the intuition behind the detection method is that binary values in SCADA system usually has a normal value and an abnormal value. So either 1 is normal or 0 is normal. So basically, we can simply count the zeros and ones and try to identify the normal value. And whenever an abnormal value appears, based on our previous inference, we actually calculate the anomaly score by this equation. As you might already notice, actually this is just 1 minus the entropy of the observed samples. So basically, we use this equation to calculate the anomaly score for the binary binary type of measurements. I think the slide ducks somewhere.
Wait, hold on.
Oh, okay.
Did it go? Wait. Oop. Where you want it?
Okay.
You want there?
It's the previous one, I guess.
Right there?
Oh, no. It's,
Forward.
yeah.
Okay. Just go. Is that what you want?
The next one, please.
I'm getting stuck on that one. I wonder if you have some, there's some hiccup there. It seems to think that's the last one.
No.
No. That.
Maybe we can quit out and try to start from.
Weird.
Yeah. One.
A little technical disruption here. Let's see if we can get it. Okay, so which slide are we supposed to be at right now? I wonder if there were any automatic thingies going on. I don't know what's going on. So that's when you want to be at?
Mm-hmm.
Okay.
Yeah.
Let me look at something really quick. No? Okay.
No, it doesn't have any.
Oh, I don't know. Maybe the batteries are. It doesn't like that slide when you. Did you put something fancy in that slide? What's going on here? All right. Oh. Hey, that's the slide, right?
Let me see if
okay.
it can.
Is it going to go for us?
No.
It's just everything's going really slow. This whole machine is deciding to go really slow for some reason. I don't quite know why.
Maybe we can.
You want to try to pick up from here and see where it goes?
Okay.
I have a question for us.
Sure.
The binary value might be 0 or 1.
Mm-hmm.
Or the binary value might be the 0 or 1.
Yes.
So what could be the anomaly value of the binary value?
Oh, by anomaly we mean like usually it should be in normal status of the system. It should be either 1 or 0, and it turns to the other whenever something happens, right? So we want to detect whenever something that's the time when something happens. So whenever it turns from its normal value to the other one, we will trigger an alarm. So that's the purpose for the binary value
or
detector.
Or if you want to confuse the operator, you make it a hat.
Yeah, so now let's talk about the analog measurement type. So for the analog measurement type, frequency, voltage, current, and power are 4 of the most common kinds, and they usually have quite different characteristics. So this 3 figures actually shows the 1 day of simulated measurements from ITI testbed. For example, we can see the frequency here is always around 60, of course for North America, and has very small relative standard deviation. And for the voltage, it's also around like a normal value, and it also has relatively small standard deviation. But for the current, it's not. And but we can expect the current to follow similar diurnal patterns throughout multiple days. So based on the different characteristics, we actually apply a 2-step anomaly detection method to analog measurement types. In step 1, we actually characterized analog measurements into different analog types further. For example, frequency, voltage, and in the second step, we actually use proper method for each type. More specifically, in step 1, we actually utilize the analog type inference model based on Bayesian network. here we used a very simple Bayesian network, which just has one root and 3 child nodes. And each child node actually has a conditional probability table encoding the prior knowledge between the child node and its parent. And the belief in hypothesis of the root is related to the belief propagation from its child nodes, and ultimately the evidence at the child nodes. Specifically, in this model, the root represents an analog type, and it has like 4 hypothesis states, and each child node here has several states as it can be observed. And if we denote yk as observation as a case child node, and xi as the ith analog type as a root node, the belief in analog type xi can be represented by the conditional probability of xi given the observation of at all lead nodes or all child nodes. That can be calculated, and this conditional probability can be calculated by these equations. Yeah. And after the analog type is inferred, different anomaly detection method is applied. So for example, mean and standard deviation are used for frequency and voltage. And for the current or power, we actually divide 24 hours to multiple time slots and calculate the mean and standard deviation in each of the slots throughout multiple days. And for analog measurements that not belong to any of the previous mentioned types, we use mean, maximum, and minimum. So notice that this list here, the frequency, voltage, current, or power, is not fixed, and you can extend it by incorporating prior knowledge of other analog types into the inference model, the previous Bayesian-based inference model, and take their characteristics into consideration while you selecting their anomaly detection method. Sure.
So the Bayesian model that you were talking about, is it only for inference, inferring the type of method?
Yes, for this.
Are you supposing finding anomalies across different measurements at all? Like, it could be that the thing between is kind of stable, but together with something else, the combination of the two things, there's an anomaly.
Oh, I see your point. So, yeah, that might be a good point. So usually, because the first sub-project here is to help us to generate the alerts and send back to the control center. And we will do the alert correlation or attack plane recognition back in the control center. But I think what you suggested is to even the correlation can help us to detect, to generate alerts at the first place, right? Yeah, that might be a good suggestion. We will consider that during our further implementation. So the alert generated by the multi-level anomaly detector is then forwarded actually to the alert manager. The alert generated by different levels of anomaly detector share common fields. The index fields, the alert types, the timestamp, confidence score, statistical field, and abnormal data. So index fields here are just like the index field we mentioned before. And the alert type is a description of the alert actually. Timestamp is when the event corresponds to the alert happens. And the confidence score is what we calculate for each alert. And the statistical field includes the previous data fields, the statistics about the data fields. For example, the current value, the mean standard deviation, etc. And finally, abnormal data here is actually the original parsed raw data, which triggers the alert. And the alert manager here consists of 2 components, the alert aggregator and the alert scheduler. So the objective of the alert aggregator is to aggregate alerts that have the same alert types, of course, as well as the alert index fields. And also they need to have little difference in timestamp to be aggregated. And the aggregated alert is called meta alerts. And the meta alert inherits all the fields from the alerts before aggregation. And each field type actually has its own aggregation rules. And also another count field here is added here to just store the number of aggregated alerts. Whenever the alert aggregator receives a new alert here, it tries to aggregate it to existing meta alerts. However, if it cannot find any existing meta alert, the new alert can merge to, it will just create a new meta alert. In this way, like consecutive duplicate alerts about the same event are aggregated to one meta alert, and which can help us prevent alert flooding and simplifies further analysis of the alerts. And every time a meta alert is created or updated, by update I mean like other new alerts are merged to it, the meta alert is forwarded to the alert scheduler. And in the alert scheduler, the priority score of the meta alert is calculated, and also like the report frequency back to the control center is decided. So the alert priority computation model is similar to the analog type inference model. It's also a Bayesian network with like one root node here, and here we have like 5 child nodes. And the root actually represents the alert priority with 2 hypothesis states, low priority and high priority. And we designed the priority score to be the conditional probability of priority equals to high, given the observation at all these child nodes. And it can be calculated in similar ways, just as the an analog type inference model. And after we get the priority score for the meta alerts, the meta alert actually we classify the meta alerts as high priority or low priority based on the score. And high priority meta alerts are always reported immediately when first created, and after that reported with a small period if they are updated during that period. And low priority meta alerts are not reported immediately upon creation, and reported with a large period if they are updated during the period. So basically now we are currently working on the implementation of the evaluation of the multi-level anomaly detector and the alert manager. And after that, we will move on to the second sub-project. So be more specifically, we will utilize alert on the alert correlation and the type recognition techniques to analyze the meta alerts. And we'll also take domain knowledge, causal relationships, and cyber-physical models of the system to aid the cause and consequence analysis of anomalies. And this is the end of my presentation. Thank you for your attention. And any question, feedback, and collaboration is welcome. Thank you.
So open the floor for questions. And those online will unmute if you have questions.
Thank you for the presentation. I think it's a very good research. I want to come back one time to the binary value. What I think is that the binary value should be 0 or 1. If I get something which is not the 0 or 1, I have to say there is an alert. So I think that's easy to solve about binary. The problem will be coming with the analog.
Yes.
The other thing I want to add is I think machine learning techniques will be equally a nice tool for computer science people to use. Because what you are doing as a research might be for comparison, for validation. So you try to, for measurement, to know what is normal and what is not normal. So I think machine learning will be a nice tool also to explore.
Yeah, actually, we explored some of the machine learning techniques, but actually, one of the reasons we did not choose the machine learning techniques is because, first of all, our framework is an online framework, so we have like real-time constraints. We want the processing of each measurement to be fast enough so it can send the alerts in real time back to the control center. And also because we use a two-step anomaly detection method, which in the first step we actually categorize into multiple analog types, and then based on the characteristics of each type, we actually do further anomaly detection. So we actually find in this way the characteristics of the types can usually be is simple enough for the mean and standard deviation or whatever statistical method to describe. So that's also one of the reasons we did not use the machine learning. But yes, if we can find some machine learning techniques that are fast enough and also good enough for any of the measurement types, we can, yeah, that's worth exploring.
When would you expect the prototype to be more?
We expect to finish this the first subproject by the end of the semester.
Okay.
Yeah, and we will start the next project in the fourth semester. Yeah, because in the summer I'm not here, so.
Right. So by sometime next year, you have complete prototype?
Yeah, I guess before I graduate in the.
When are you?
Probably end of this year or in early next year. I hope so.
Okay.
Yeah.
Getting back to what Prosper had brought up, the problem with a lot of these anomaly detection software schemes are that they give you lots of that say things are abnormal and they're not.
You mean false positives?
Yeah. To the point where people turn them off because they're nuisance.
Yeah, actually.
How do you avoid that? I mean, how do you make it so that any anomaly, any detection you get is 99% guaranteed to be a true anomaly?
I think to achieve that, we need the feedback loop from the operator. Like we need to. That's also like part of the plan. We want to have a way for the operator to give feedback to the system. Because when, for example, when the operator actually sees this alert actually and decides this is actually a false positive and can tell the system that is a false positive, so the system can adapt to avoid generating the same type of alerts. And the same applies to the measurement inference, the analog type inference. Maybe if the operator can help the system to identify some of the important analog types, that can also help us to build models with more accuracy.
So the way I see it is you have the more like a taxonomy of things that could have anomalous behavior in the system that you're saying, I want to use this technique on this data, this technique on this data, aggregate it at one place, and then somebody will provide me feedback about what's wrong, where the system is incorrect, right? But why don't we look at the entirety of the content of the package? Like, are there models where you can look at, so ultimately you're collecting data from a stack, right? So CCAP, where you're collecting all this data. Or
if you do offline analysis, yes.
No, even for online, you'll be collecting data from the network, right?
Yeah.
Are you planning to integrate anything from the system the CPS that is running?
You mean like system logs, things like that?
Yeah, system logs.
In the current project, not no, but like this is where the flexibility of this project actually comes into play. Like for example, as long as the meta alerts we generated by our first part of the project and the system logs can be like converted to the same have the same structure. The further the analyzer, causality-based analyzer, can take them both as inputs, as long as you first convert them into the same have the same structure. So
there is a structure, like there is an underlying structure. It's a big thing. the packets that you're collecting, the data that you're collecting, is a stream of data. Right?
Yeah.
What you're doing is you're going back and saying semantically, this is this field and this is this field, this is this field. And then you're finding anomalies within those parts of the packet. Right?
Yes.
Have you thought about having like a model which just takes the entirety of the packet and finds anomalies and fix the patterns that you see? Because these systems, they don't have, the dynamics are pretty irregular, right? So if your fixing is going.
Are you talking about like instead of like dividing the data into multiple levels, just use one level and to do all the things?
Yeah, like if that, have you thought about it? I'm just trying to, basically just thinking you're fine, because your approach is divide. Do specialized techniques for each one.
Yeah, but actually, as I mentioned before, like different levels of data have like different characteristics. For example, in the transport level, in terms of inter-arrival time, so you can consider it as like follows a multimodal distribution. Because consider the example that you send the control center send a read request, followed by a response by the field devices, then the control center send the confirmation. So the inter-arrival time between the first read request and the confirmation is very short, but the inter-arrival time between the confirmation and the next read request could be very long. And so there could be like multiple valid mean values for the inter-arrival time in the transport layer. But in terms of the operation level, if you consider the inter-arrival time of the same operation, so for example, all the read requests from the master stage unit to a single field device, they usually are periodic. So they usually has a one valid mean value. So in that sense, we need to use different methods. So that's why we use the clustering method for the packet processor and the mean and standard deviation for the operation level. So if you want to consider all the data just using one method, it could be possible that the method you selected is optimal for some of the levels of data, but not suboptimal for the others. So yeah, that's the reason we want to divide it into multiple levels and differentiate them first before we do the anomaly detection.
That's right. If I understand the word, the tool you are designing is a real-time tool, or you are expecting to collect the data in real time?
Yes.
From the test bed, right?
You mean the traffic?
Where do you get those data in real time? Where do they come from?
Oh, the current data, we haven't done the evaluation yet. Okay. So, but I guess for the evaluation, I don't know whether we are able to do the evaluation in real time or not, but we are definitely going to evaluate the processing delays for different components, so to see the capability of this framework to be run in real time.
Okay.
Yeah.
Any other questions?
I guess one last thing. The state estimator that we use has a thing called bad data detection in it, throwing away what is considered bad data. And the criteria for that is probably something you might check into, or at least be aware that there already is a set of software that gets into the SCADA information, processes it, and says this is bad, throws it away. That already exists as part of the commercial code. So you should probably check into that and see how it relates to what you're looking for. Did you talk about what you're going to do when you find a piece of abnormal data? I know it was in your plan, but I didn't hear you talk about it. What's going to be the suggested remedies for the anomaly?
Yeah, that's the next step, the project we are going to work on. We haven't touched that part yet. Yeah, but I guess we will probably use like to correlate, because previously we just do the generate alert in each of the levels of data, but there might, like, by considering all the levels of alerts together, we might be able to find some identify some attacks which we cannot by looking at just one level of alerts. So we need to use some alert correlation techniques, and also like probably by that we can try to figure out the attack plane of the attacker, and yeah, also based on the attack plane, maybe we are able to suggest some responses for the operator.
Are there any questions online? Okay, you have a couple minutes for people. Okay, well, let's thank our presenter.
Thank you.